Okay, so finding that block is kind of time consuming. You just have to go and have a look for it. Now, imagine if you have to do that for every block in the entire frame. That's quite time consuming. If you didn't find the block and someone told you where the block is, like when someone tells you where it is, it's easy enough to get it. And that's the difference there in the compression and the decompression that causes the asymmetry. Finding those blocks is very time consuming in comparison to just actually going there and getting it. If someone says to you, it's this many pick, this many up, this many down, you just go get it. So it's very like Where's Waldo or Where's Wally, depending on where you are in the world. So someone tells you that Waldo's in there somewhere. So you're a video compression algorithm and you have a block of pixels. It turns out we only use 8x8 blocks, and is it 8x8 or 16? No, 8x8. And we only use the luminance actually. We only bother searching on the luminance. We don't bother considering the chrominance. But someone says to you, he's in there somewhere. The block you're looking for is in there somewhere. And that's pretty much all you've got. You can go, through it slowly and eventually find it. Once you've found it, saying to someone, oh look, copy and paste him there, he's over there by the fountain or whatever, Oh, he's by the fountain, in fact. Okay, where is he? I don't know, where is he? Oh, there he is. So when someone tells you where he is, it's easy then to find him. And so the video compressor the video transmitter is saying to the receiver, go get that block from position 420 or something. Going and getting it is very easy. It's finding it in the first place is what's hard work. And that makes video asymmetrical. So I'm going to talk about now how this is done and the algorithms that are used to make this more efficient. So first of all, it's only done with the luminance. So it separates out the luminance and the chrominance and only considers the lightness and darkness of the pixels. But it's still a very difficult thing to do. If you're a computer program and someone says to you, this block here is available somewhere in this image, go find it. That's an awful lot of work. It's actually much easier for humans, in fact, than it is for machines. Because we can look for, features that stand out or whatever. And so that's the block matching problem, it's called. How do you find this block in this image so you can say to the receiver, go copy and paste that from position whatever. So, like I said, it's not an easy thing to do. You actually did it much faster than I thought you would. I think this big block of 4 here made it easier. So what a computer would have to do is look here and see, is this a good match for that? And the answer is no. Is this a good match for that? 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 And that's all a computer can do. That's all an algorithm can do. And you can see that would be quite time consuming. Now, it turns out it was down here, it would have found it eventually. And of course, it's probably not even going to find a perfect match. It just wants to find a good match. So usually what happens is the search area is confined to a small area centered on the location in the current frame. So if you had an algorithm that was looking for something that looked like a plane on satellite images, you would probably center the search around where you actually expected the plane to be, for example. So if the target block, the one we're trying to code in the current frame, is at position XY, then we might make a search area in the previous frame centered around that position XY. Because we know, for example, if there's only 25 frames a second, well, how much can something have moved really in 1/25th of a second? I mean, it's still an actual object moving in real space that we've recorded on video. So it probably hasn't moved that far. So we use then a matching function to score each candidate. So don't be freaked out now by the representation here. So this is the mean absolute difference. And basically, you take the first pixel in the target block and the first pixel in the candidate block. You subtract the value of one from the other. And then you just do an absolute of that. So if it was -7 or +7, it gives you 7. And then you add up all of those differences over all of the blocks, and that gives you a score. That's all this says in math speak. So we go from Q1, Q goes from 1 to N, P goes from 1 to M. We just sum up the differences between them. And we divide that by the number of things there. That's all that says. So I think it's easier to understand as an algorithm than it is an equation. That's the mean absolute difference. So you take the difference between the pixels and absolute it and get the average of those. So if we look here, I think I'll preface by saying there's a deliberate mistake in here somewhere. But I think I made a mistake here somewhere, but we'll check. So for simplicity here, I've got 5 different intensities of grey. Now we know that most images and a video would have 256 shades of grey. You go from 0 to 255. But we probably wouldn't be able to see the difference between 251 and 252. Okay? So let's say this is our target block here at the bottom. Let's give each of these candidate blocks a score. Now in reality, the blocks would be 8 by 8 pixels. But again, that's the same, just more math. So the difference here, we have 3 minus 2 will give us 1. Between this pixel and this pixel, it's 3 minus 2 again, which will give us 1. The difference between this pixel and this pixel is, according to this, it's 0. They look quite similar to me, but it could be an optical illusion. They look different to me, but I think that's just an optical illusion. Between this one and this one, it's 3 minus 3 is 0. 3 minus 3 is 0. Between this one and this one, we've got 4 minus 3 is 1. So the difference between each pixel, here we've got 0, minus 1, and 0, minus 2. So the value for this one is 6. So the mean absolute difference here is 6. In this case, we're comparing again pixel by pixel. We compare each pixel in the target block with each pixel in the candidate block, subtract one from the other, get an absolute of that, and just sum them all up. So where there's a difference, it's going to be added to the score. And we keep going. So in this case, the mean absolute difference gets a score of 11. Now in the equation, we actually divided that then by the number of pixels. But it doesn't really matter. So in this case, what do we think it might be? Do you want to hazard a guess at that? Do you want to see if you can work it out? I think it's hard actually, even with 5 shades, to visually compare them. How about we just decide whether it should be better or worse? How about that? Do you think it would have a higher score than 11? Do you think it's more like the target block than the other two? Or not? That's even a hard one to answer, isn't it? Let's see what past column says. Okay, so if we put in the values here, it's easier to work out. We're not relying on it visually. So work out the MAD, the mean absolute difference for this block. You could do it on your fingers even. What did you get? So compare each pixel with the corresponding pixel and get the difference between them and add that to your total. It's clearly time consuming anyway, which is the point I was trying to make earlier. I got 10. Anybody get 10? I'll show the ones. So we have like 2 plus 2 plus 0 plus 0 plus 1 plus 3 plus 0 plus 0 plus 2. So according to this scheme, it's a better match than the middle one, but the first one is the best match of all. So the lower mean absolute difference is the best match. No, I don't think any of them are particularly good. Okay, no. So this one has the lowest mean absolute difference, so it's the best match. Now the mean squared difference is similar, but in this case we don't subtract one from the other and absolute it. We subtract one from the other and square it. So if the difference was -4, the value 16 gets included in there. And what that does is it penalizes big differences. So if there was a difference of 2 across 3 pixels, that would be 4 times 12. If one of those was, say, had a difference of 4 and the other two were the same, it would consider that worse because it would be 4 squared, which is 16. So it penalizes big difference. It exaggerates any differences that there are. And this is a different measure, but it does roughly the same job. Would anyone like to hazard a guess whether it's better or worse? Does it come back with better matches or worse matches? People say it comes back with slightly better matches, all right. But one of the problems with it is that it's much more computationally intensive. Squaring things, any kind of multiplication, for the computer scientists among you, is obviously much more work than an addition and a subtraction. So multiplication squaring is a costly operation. But generally it's considered a better metric. So the mean square difference is a better measure in terms of accuracy, but it's more intensive. And of course the problem is you're going to do this hundreds of thousands of times. So if it gives you slightly better matches, but is maybe 10% slower, takes 10% longer, you might say, well, sure, it's only going to take, what's the difference between, 10 nanoseconds and 11 nanoseconds? It's only 1 nanosecond. Yeah, that's if you're doing it once. If you're doing it millions of times, which is what you're going to have to do, then the difference between, 10 hours and 11 hours is all of a sudden another hour. In the early days of video compression, it was so computationally intensive that you didn't even attempt to do it yourself. You would send off your videotape like you used to send off your photos. And a week or two later, your compressed file would come back. Nowadays, we attempt to do this at home on our home machines. And actually, my iPhone even attempts to do it before it sends something off. If I try to email someone a video or post it somewhere, it'll even have a stab at compressing it. But it was so computationally intensive that it was a specialist thing. Well, that kind of made sense. It was always going to be the BBCs and the RTEs of this world that would be doing the compression. So you wanted to put all of the effort, all of the intelligence into the compression part and make the decompression as simple as possible so that receivers would be cheap. So it's no accident that video is asymmetrical. And this is what makes it asymmetrical, all of this work. So even if you only allow a block to move a small amount, the number of candidate blocks you have to look at can be quite large. So let's say we had an image, it's like maybe 1080 pixels by whatever, 900 high or something, that's our screen. And if we said between one frame and the next, we're only going to allow a block to move 30 pixels in any direction. That still gives you 3,721 candidate blocks that you have to evaluate. So evaluating each block is known as the brute force method. And that's expensive, which means it's slow. So what we'll do in the next class is we'll look at some of the ways that we can make this work without having to compare all of the blocks. But I think your heads have been expanded sufficiently for one class today. So you'll be ruined now. You won't ever be able to look at a JPEG or look at a video again without seeing these things. You'll actually see the blocks. So we'll pick this up in the next class. Thanks, guys.